Imagine standing at the southern tip of South America, watching the Pacific Ocean and the Atlantic Ocean meet. The water seems to clash like two rivals, creating a visible boundary where the two oceans refuse to blend. It's a mesmerizing sight, but why does it happen? Do the Pacific and Atlantic Oceans really not mix, or is there more to the story? And what does this divide mean for the marine life, climates, and ecosystems that depend on these waters? Let's dive deep into the science behind this natural phenomenon. To begin, let's address the most common question: do the two oceans truly never mix? The short answer is they do, but not in the way you might expect. At the surface, the Pacific and Atlantic Oceans can appear as if they're entirely separate, with clear differences in color and texture. This visual divide is a result of physical and chemical differences between the two bodies of water. But if you go deeper, literally, you'll find that the two oceans are constantly exchanging water, albeit slowly and under specific conditions. So, what causes this striking surface boundary? The first and most important factor is salinity. The Atlantic Ocean is saltier than the Pacific Ocean. This difference in salinity creates a variation in density. Saltier water is denser and tends to sink below fresher water. When the two oceans meet, the denser Atlantic water often slips underneath the Pacific water, creating layers rather than an immediate blend. This layering effect leads us to the next factor: temperature. The Atlantic and Pacific Oceans often have different temperatures, especially where they meet at key points, like the Southern Ocean near Antarctica. Warmer water is less dense than colder water, which can amplify the separation caused by salinity. But here's where it gets even more fascinating. These temperature and salinity differences don't just stop at the ocean's surface. They extend into deep currents, creating what scientists call a thermohaline circulation, or the global conveyor belt of ocean water. Now, you might be wondering, if they don't mix easily, how does this impact marine life? The answer lies in nutrient availability. At the boundaries where the two oceans meet, upwelling currents bring nutrient-rich water from the deep ocean to the surface. This creates thriving ecosystems, such as those found near the Drake Passage, where krill, whales, and countless fish species flourish. These boundary zones act as hotbeds for biodiversity, but they also highlight how the ocean's inability to mix freely shapes marine ecosystems. But let's zoom out for a moment. Why are the Atlantic and Pacific Oceans so different in the first place? Part of the answer lies in their geological history. Millions of years ago, the Atlantic Ocean was much smaller, while the Pacific was the dominant ocean on Earth. Over time, tectonic activity, such as the formation of the Isthmus of Panama, reshaped the global ocean system. This narrow strip of land separated the Atlantic and Pacific Oceans, disrupting the free flow of water and creating two distinct ecosystems. Before this event, water and marine life freely moved between the two, creating a more uniform global ocean. Another fascinating aspect is how these differences influence weather and climate. The Atlantic Ocean is a key player in the Gulf Stream, a powerful current that transports warm water from the tropics to Europe, significantly influencing its climate. Meanwhile, the Pacific Ocean drives the El Niño and La Niña phenomena, which have global impacts on weather patterns. The fact that these two oceans don't fully mix means their unique systems remain relatively isolated, amplifying their distinct roles in global climate regulation. At this point, you might be asking, what about humans? How have we used or studied this natural oceanic boundary? For centuries, sailors and explorers have been captivated by the dramatic differences where these two oceans meet. In the age of exploration, these boundaries posed significant challenges, as different water densities could create unpredictable currents and dangerous navigation conditions. Even today, scientists study these boundaries to better understand how the oceans regulate the planet's climate and how human activities like pollution and overfishing are affecting these delicate systems. One of the most striking visual examples of this oceanic divide can be seen in glacier-fed fjords in regions like Alaska or Patagonia. The fresh water from melting glaciers flows into the saltwater ocean, creating a similar boundary effect to what's observed between the Pacific and Atlantic Oceans. These natural experiments give scientists a smaller, more controlled way to study how different water masses interact. But there's another side to this story: climate change. Rising global temperatures are altering the salinity and temperature of the oceans. Ice melt from Greenland and Antarctica is introducing vast amounts of fresh water into the Atlantic, potentially disrupting its density-driven currents. If these changes continue, they could weaken the Gulf Stream and other critical systems, leading to dramatic shifts in global climate. Could the natural divide between the Pacific and Atlantic Oceans disappear over time? And what would that mean for the planet? Let's bring it back to where we started. The apparent boundary between the Pacific and Atlantic Oceans isn't just a natural curiosity, it's a testament to the incredible complexity of Earth's systems. While the two oceans may seem to repel each other, their interactions drive weather patterns, support marine life, and regulate global temperatures. Understanding these boundaries isn't just about appreciating nature's beauty, it's about recognizing how interconnected our world truly is. If you found this exploration of oceanic boundaries as fascinating as we did, make sure to subscribe for more deep dives into the mysteries of science and nature. And let us know in the comments, have you ever seen the Pacific and Atlantic Oceans meet? What questions or thoughts do you have about these incredible natural systems? We'd love to hear your perspectives.